Alright, time for another draftphysics.com, debatephysics.com also. Please, debate. Uh, and video presentation. Yes, just can't get anybody to rationally respond to any of these arguments. So I'm going to make a few more arguments. And no one will diagram my mistakes or how I've misrepresented the truth or any of that. So we're still on the same subject for 4 years now, I guess. And the fact that there's, regular conventional physics has not done any experiments regarding trying to tease the truth out of reality. What's more important, momentum or kinetic energy? Scalar energy, motion in no direction. Anyway, and so there's all these, they can make lots of statements, but because there is a lack of decisive evidence, they can just make stuff up and say it happens and nobody questions it. And that's the part where you say, oh, okay, it isn't science, because scientists aren't supposed to just accept crap. They're supposed to say, show me, come on, give me some real information so I can see it myself and understand what you're saying is true. So the implications of the kinetic energy theory is what I've stated so many times before, that it takes 25 times the fuel or motion or energy to make something go 5 times as fast. And that something going 5 times as fast will do 25 times the work. Not 25 times the nothing, 25 times the work. It'll actually produce some kind of effect. Okay, that's 25 times more than the effect it would produce if it was going, say, 10 versus 50. So they're saying something going 50 miles an hour will do 25 times the denting, smashing, crushing, killing as something going 10 miles an hour. And there's absolutely no evidence that's true. And all crashing of car analysis is always by momentum. So if you go find some channel that analyzes car crashes, all they talk about is the momentum, because that's all that's going to dent things, that's all that's going to smash things, that's all that's going to push things, that's all that's going to be involved. So, I mean, it's just, that says it all right there. Their physics says that, a one mass going 10 velocity is the same thing as a 4 mass going 5 velocity, because it calculates out to be the same thing, not because anybody's seen it to be the same thing. So if you had a car crash with something that was a 4 mass, okay, 4,000, doesn't matter, you can 4 anything, going half the velocity of one mass going twice the velocity, everybody knows that the 4 mass is going to decisively win. It's got twice the momentum, and you have to pay attention to momentum. I mean, they say momentum has to be conserved. They say Newton's third law is relevant, and yet they just completely ignore it when convenient to defend a silly formula that was never codified, or it was never knighted. It never became a lord. It never did anything. It never passed any test to qualify it as great science. It just hasn't. It didn't. It's just a fact that it's a fable. It's not anything scientific. All right, so we'll just go through the lever first. I'll explain why their assertions are incomprehensible to me, okay? And until I see it, I ain't going to believe it. And then I'll explain some other defects in experiments that, you do have to understand that every experiment's got other variables in it, and you have to control for variables. So I've talked about that before, but it really is important. Yeah, we'll see where else I go. I mean, I'll try not to be redundant, but yeah, some of this has to be redundant because none of these arguments have been addressed in any way whatsoever. All right, so I'll get to it. All right, back. So let's just start with the basic lever, and we'll just explain a couple of possible variables that we'll account for. So let's just assume it's a sticky, that there's a Velcro, so this sticks. It's not going to bounce if you do all these measurements correctly, but obviously if you create a circumstance where the lever does actually change the force it's applying, there's a possibility of a bounce. So if it feels the thing on the other side is heavier, okay, then if it senses it to be heavier, that is, if I move the 2 mass further over, this is called those 2 mass, and we'll call that a 1 mass. It's going to behave differently in the sense that it might bounce off the lever because it can't move the heavier object at the same speed that it's going to decelerate. And these lines are just to represent that at 1 unit of distance from the fulcrum, it's 1 velocity. At 2 units of distance, it's twice the speed, twice the movement of the matter. So let's just say first off that these 2 things aren't here and we're just going to hit the lever. You have to concede that, well, this part of the lever is going to move 1 velocity, that is the mass here, and the mass here is going to move 2 velocity. And there's not going to be anything that's going to stop that from happening. The same thing is going to happen over here. This part of the lever is going to move twice the velocity of this part of the lever, and this part's going to barely move at all. And that's a proven over time fact, okay? So, and you will put a certain percentage of this thing's momentum will just go into moving the lever, and that'll be the end of it. The lever will swing and it'll rotate at a speed probably the same, close to the speed that the object had if it's much heavier than the lever. But the lever will absorb some energy, and you can figure out exactly how much energy the lever absorbs by actually spinning. All right, you're giving the lever momentum. And if you were to launch these objects, obviously you might want to put a stop somewhere on the lever. Okay, so they leave, without getting swung, in some 90-degree angle. You're trying to just launch them semi-straight. Okay, so obviously the stop means that the stop will collect the energy that the lever had in it, and so it'll all be conserved in the end. All right, so it can move this part of the lever, isn't going to stop the lever. There's no inertia in this mass, right? So there's no masses here, just the lever. No one's going to argue that the mass, that this part of the lever right here has more inertia. That somehow there's an inertia problem and you can't move that part of the lever at twice the speed and you're going to consume more energy somehow. There won't be any more conserved. There won't be any more used. It'll just be figure out what the total mass is. That's their own mathematics. Figure out what the total mass is and then figure out what the average center of mass would be, and it's going to tell you exactly how much momentum the lever is going to consume, and they can calculate it and predict it, and it'll be accurate. And they won't be predicting it based on some notion that this part of the lever can't do it, that it only goes 1.4 because it can't be moved twice as fast. No, the matter here can be moved twice as fast with this just using twice the energy. That's all it's going to take to move this part of the lever twice as fast. So anyway, let's do the experiment. So let's just pretend the little one isn't here and we're just doing the big one. So you can understand that what's basically going to happen is you're going to be able to see it happening. Is that this thing hits, okay, they could do this with a slow motion camera and you could see it. This one's going to start decelerating as soon as it hits the lever, right? So its acceleration is going to go from its peak to its bottom, right? And the 2 mass is going to do exactly the opposite, right? It's going to go from, where's the best way to draw that? It's going to go from the low to the high, okay? So it's going to basically exchange the energy. Now we know we're losing some to the lever, so some percentage, whatever, 5%, who knows. I guess it would be 5%, not 0.5, but anyway. Well, you can't see that anyway. Pretty clever of me to make it invisible. Anyway, so the lever's going to consume some of the energy. So ideally you move this in just a little bit, okay, to compensate for the fact that you don't have, because you're losing some to the lever, you don't have the full volume of energy. So if you want to be able to move that other object at the same speed, you need to move it in a little bit to make it a little tiny bit lighter so it'll go the same velocity. All right. But the idea is you put this in with a velocity, and you're going to get the same velocity out of the same massed object. So that's pretty simple. We all should be able to agree that substantially you're going to conserve the momentum and get out what you put in minus the losses to the system. All right. Now, and again, the accelerations and decelerations will match. All right, so now let's just do the other one. Okay, so now the other case is this lighter mass, half the mass, at twice the distance. Again, we can compensate for the fact that we're going to lose a little bit to the lever. And so what's the expectation? Is that, they're saying instead of going 2x, instead of doing this, it's only 1.4, a substantial degrade. I mean, it's, 0.6. It's 30% of the momentum is gone. Okay. And they don't give you any explanation for where it would go. And the simple argument is this is going to decelerate at exactly the same rate. They admit that the force here, right? So if I measured the force here, it'll be exactly the same force when this thing's here and when this thing's here. Exactly the same force. It weighs exactly the same. They concede that. And yet somehow this behavior is going to be completely different. Somehow it's not going to decelerate at this rate. It's going to decelerate at some other, let's see, which way should I draw it? It's going to decelerate slower, yeah, and less severely. Well, I can't do it less severely. It's going to be a longer sloped line, okay, because somehow it's just not going to be able to get to that velocity, and it's not going to be able to transfer. Its deceleration isn't going to match the acceleration. Now, my simple argument is obviously it's the same force. As this decelerates 1 unit, this one accelerates 2 units. That's the obvious thing, right? 2 units here, 4 units here. 3 units here, 6 units here. Okay, it's going to be exactly twice because it's twice the distance, it's twice the velocity, and there's not going to be any problem it going twice the velocity. There's no rational way you can argue there's a problem now. All of a sudden it can't do it. So another test for all of this is to do the experiment with the one object on the lever and then put both objects on the lever, okay, and see how much energy you need to achieve the same speed. Or just say, well, what's the velocity of these two objects? Is their velocity 1/2, okay, of the velocity they had when done independently? And that will tell you the truth. So you just measure this velocity. If it's 1/2, the velocity when only one. If it's 1/2, the velocity when one object is on, and then you put 2 objects on, and it's half that. Well, then you know this didn't consume any extra energy. So I mean, there's no counter argument. I haven't heard anything. There's nothing explaining how somehow there's some magical inertia thing that stops the mass from moving twice as fast. There's nothing. They don't have an explanation for it. They just say it happens. Alright, so in Steve's video where he's saying levers don't conserve momentum, that somehow the lighter mass can't be moved twice the velocity, that it can only go 1.4, not even 1.5, not 1.6, not 1.7, not 1.8, not 1.9, no, 1.4. Okay, so way short of its what you would expect if you were rational, And so he puts a clip in the very video where he's claiming this other thing. He puts a clip in that proves the case that pulleys do conserve the momentum, no problem. That moving the lighter mass twice the velocity, no problem. Same exact force applied. So you can just see it in the drawing. The 10 newtons, 10 newtons. So the half mass would be on the right side. The full mass would be on the left side. And what will basically happen if you use the double pulley, doubling, okay, your advantage. They call it a mechanical advantage. It's not a mechanical advantage. It's a simple conversion. You're just converting the momentum. And that's all you're doing. And so you use the same amount of energy and you move the half mass twice the velocity. So he proves it mathematically, shows it overtly happening in the very same video where they're supposed to be arguing that the half mass can only go 1.4 and that the pulley on the left should totally fail at being able to create the same momentum with the same force in. And so it doesn't make any sense. So 1 million views for the video, and I'm the only person that's pointing out that that makes absolute zero sense. It just, how can anybody defend that as anything other than they can't even they can't even organize their religion into a coherent story. I mean, 1 minute Jesus is a god, and the next minute he's just a man. That kind of nonsense. Miracles are supposed to be taken with a grain of salt, or oh no, they're literally happened. The sun stopped, in the sky, and nothing else happened. It just stopped, and there's no consequences. So that's all. They're just showing they're just making it up as they go along, and they're not even paying any attention to the premises they're arguing. I mean, to have this other guy introduce an opinion, and his opinion is completely the opposite opinion, but he pretends, oh yeah, I totally agree with you. The momentum is completely conserved. Yeah, well, even though you're arguing that the momentum isn't conserved. I mean, it's just so bad. And the fact that you people will continue to defend something this plainly ludicrous. This isn't even close to being science. It's so ludicrously contradictory and nonsensical. It's an idiotic argument. There's no evidence that levers don't conserve momentum. The law of the lever was 2,000 years old when Leibniz decided to invent this V squared term. Okay, and all of a sudden now, 300 years later, you start telling us that levers don't work. So for the 300 years, you just kind of pretended, well, let's not talk about levers and let's not talk about basic tools because they don't demonstrate kinetic energy to be real. And now you're trying to say they do demonstrate it, but you have zero evidence. And so you're just making religious claims. You're not making scientific claims. You're not just debunking my assertion. You have to explain how for 2,000 years they had it all wrong. Okay, that levers don't conserve momentum. And again, the more dramatic the lever, the more dramatic the difference in terms of the distance it uses, the more momentum you lose. So at a 5-to-1 or 6-to-1 ratio, you're starting to lose in the 90s of the percentage of your momentum. And it just doesn't make any sense that you people will keep defending this nonsense as science. Good science. This is horrible science. And you're all a bunch of... I mean, you can't... I could call you ignorant and stupid, but you're a lot worse than that. Because you're doing it belligerently. The facts are clear. This is junk science. You should call it what it is and say, I want a redo. I want it done right. Alright, so as part of the irrational defense of nonsense physics, people keep arguing that I'm denying experiments when I point out huge flaws in the reasoning behind the experiment. So every experiment has loopholes, okay, and as has been proven over and over again, by undeniable rational analysis. Okay, I mean, it's an undeniable fact that if I roll something at twice the velocity, so we'll put the twice the velocity on top this time, it'll roll 4 times as far. Okay, and that's just a reflection of the gravitational reality. All right, that 4 times the height only gets you twice the velocity. And what's, you could just, like I said, this is an undeniable fact that one velocity, which is this one, okay, will happen here. That's where one velocity happens, because we know this and this have to be the same. There's just no way around it. You can't be going one velocity and go any further than this. So we know that this is one velocity, okay? 3/4 of the distance is one velocity. So we know, all right, the friction isn't linear. That's important to understand. Okay, so people have done experiments where they launch things with, say, a spring, and they have one thing going twice as fast as the other thing. And what they do is they let them travel some distance and then hit a target. So they're obviously, you can understand that, well, if the total distance they would have traveled is this, okay, and this, let's say, it's going to be even more dramatic than that, actually. So it's going to be an even more dramatic difference in their distance. I mean, I can't even, realistically draw how dramatic, because it's as dramatic as this. So they're doing the test, say, at this location, right? So they're saying, so obviously this thing is almost out of all of its energy. It's rolled, it's lost almost all of its energy. This one still has 3/4 of its velocity. It still has a huge percentage of its velocity. So obviously, yes, the one on the twice as fast object and the one object is going to have a huge disadvantage. So the heavier thing or the slower thing is going to be hugely disadvantaged if you're going to do the testing here. I mean, obviously you have to do the testing right when they leave, or there's no point in doing the test, because they lose energy at a grotesquely different rate with distance. So, I mean, an obviously silly experiment, right? So somebody does this experiment, like they put a cracker over here and say, look, I'm going to smash the cracker. I mean, obviously it's a huge cheat. All right, so I'll get into the pendulum argument now too. But just understand that's a real variable you have to understand. It's not a fake one. It's a real circumstance that makes the experiment almost laughably irrelevant to the truth. And so I've pointed out about springs. I mean, and I'm still getting people arguing that somehow this is not a legitimate argument, but there's no explanation for how it's not a legitimate argument. Springs have this flaw, that if you're pushing a big thing, okay, or you're pushing a small thing, the fact is the spring is moving at the same speed as the object is pushing. That's how it works. It's giving it the momentum by actually moving the object and sticking to it. And there's a point where the object leaves, and it's going to have a velocity. So let's say this has a velocity of 1, and this is going to have a velocity of 10. Now, the truth is, when this little thing gets thrown off, the spring is still going. When the velocity of the object is 10, the spring is still moving at 9. 9.9. Right? I mean, that you can understand. The spring doesn't just stop once it goes 10. The spring doesn't just say, stop, I'm done. No, the spring is still moving. So the mass of the spring is still has energy to give, but there's nothing to give it to, because the thing it was giving the energy to is now going faster than the spring is, because the spring's losing energy as the object's gaining energy, and those two lines cross. And once they cross, it doesn't mean everything else disappears. No, the spring still has more to give. It just can't give it because it can't hit the damn thing because it's going too fast now. So the spring obviously retains a much more energy here than it retains here. All right. So this is not a destructible argument. There's nothing tainted or biased or inaccurate in this simple description of a variable you have to appreciate. That every time you use a spring, whatever the spring is made out of, whatever the density, the mass of the spring, you have to consider the fact that that spring is going to retain some amount of energy. It's always going to retain some energy. There's no velocity I could push it at that's zero velocity. So I can't possibly not lose some energy. But with a heavy thing, it's almost a minuscule loss. And with a light thing, the lighter it is, the more I'm losing, because I'm just left with the maximum velocity of the spring. Ultimately, the spring can only move so fast. It has a limit. There's air. It's pushing air. That's its maximum speed. Technically, I could put something very light on there, and I'm not going to get that. That speed is not going to be the total momentum you stored in the spring. It's just not going to be there. So it's not going to be able to give it that. And as I stated, to give it, it has to do it. And the fact is, the object's going to leave before the spring's done springing. So the spring's going to oscillate, demonstrating how much energy it's retained. Fact has to be appreciated. All right, so there's lots of ways to do experiments. Now, the real problem of, I've been over the angular momentum one so many times now. Whether you're rolling an object or whether you have wheels. Okay. Now, the advantage to wheels is that if you crash something that has wheels and an axle into an object, the angular momentum will be converted into forward motion. But if it doesn't have an axle and it's just a rolling object, well, then you can understand that the motion that it's going to make contact with the surface is down. So in this case with the car, the motion of the wheels is going to be in this direction. That's the contact direction. And the contact direction here is going to be down. So if you have a spring or something, it might just push your spring down. It's not going to push it in. It's going to push it down. So you're not going to gain, you're not going to collect all of its energy because you don't have a mechanism to convert it into this way instead of down, okay, because of the rotation this way. All right, and so the point is that you can understand that whether it's a rolling thing or it's a wheel, that the rotation is part of the energy. Okay, so it has two kinds of motion. It has its linear momentum. I mean, that's velocity in its actual space, how much it's moving. But the wheels are always just flywheels. So it's the same thing as me just having the flywheel on top spinning and using that and saying when the thing hits, I'm going to now stop the flywheel and force its energy to also push. So the fact is every time you're creating a car or a rolling object, you have to account for the fact that you're putting more momentum into it than you think. Its linear motion is only a part of its motion. The other part of its motion is its angular rotation. And they're two separate hunks of momentum. And in one circumstance, if you do it right, you can collect both. And in another circumstance, if you're just measuring velocity and friction, you're not going to measure both. So it's, you have to understand there's a fair way and an unfair way to test for how much total energy it actually has. And you have to recognize that to make it roll, you had to put more energy in. And to collect it, okay, you have to recognize that its linear motion isn't all of the motion it's stored. So if I have two carts, the simple argument is if I have two separate carts and they're going two different velocities, okay, the obvious fact is if I measure their linear motion, I'll get maybe it's going twice as fast, right? It's got twice the velocity in linear motion. But the catch is, okay, 1V. The catch is that, yeah, it's going twice as fast, got twice the linear motion. That is, I'm measuring its motion. But the fact is, this has twice the energy stored in the wheels. So if your wheels are heavy, dense, then you've stored a bunch of momentum in the rotation of the wheels. And that's going to make a difference when I crash these into surfaces. This one's going to measure as more energy because it has more angular motion in its wheels. And if I assumed when I launched them that, well, this one was half the mass and this one was twice the mass and it should go twice as fast, well, I have to recognize to make it go twice as fast, I have to put twice the energy in the wheels. So it's going to consume more energy to push, and it's going to, depending on how I collect the energy, I'll collect more momentum. Okay. When I collect it, then the linear motion says it has. It's going to have more energy than the linear motion says exists. So these are all real variables again. So these are the people defending science, and they don't think that's a scientific argument. That nobody should pay attention to the fact that, yes, that's exactly how wheels behave. That their motion is completely independent. Their angular momentum is completely independent of the linear velocity because they're just going round and round and round. They're going in all directions, okay? busy going in all directions. It's mass moving in all directions, round and round and round. It's mass moving in all directions, okay? It's not moving that way, it's spinning, all right? And the fact is, it's a real variable. It needs to be understood and appreciated. And again, it's one of the reasons I'm saying to you, they make these carts for these experiments and they deliberately manufacture them to have way too much momentum in the wheelbase. So they put metal wheels with metal axles just to create more angular momentum in the wheels. It's not the way you would, if you were saying make me a low friction car, your idea would be not to make the wheels out of any kind of heavy material. The idea would be to make the wheels as light as possible to eliminate any angular stored momentum. So it's just, I mean, you can't call it deliberate, but it's just, they're trying to present physics. They're not trying to show you physics or trying to explain or reveal physics. They're trying to teach you what's in a book, and they're trying to show you that the book is right. And so they're deliberately manufacturing experiments that have these catches to them, and they're just pretending there's no catches when there's plenty of catches. Using springs, catch. Using wheels, catch. Okay. All right, so that's what just makes all this tricky, right? Because I could say, okay, how do I do this experiment? Let's say I got a lever and I just want to push something with the lever, right? Now, if I'm going into gravity, well, okay, that's a little messy, because then we have to figure out how much gravity is affecting something and 4 times the distance and all this nonsense. So it'd be nicer to get that out of the equation. But to get that out of the equation, then you're stuck with, okay, well, how do I measure actual just the linear velocity and nothing else? And so a test you could do, right, is that I can show that, I think. So the point is that there has been experiments done. Somebody took a cue ball, a billiard ball, and to get a half mass he just cut the extra bits off, and so it's the same surface, and then you put it on glass, so it's really a slick surface. And so there was very little roll. The twice as heavy one rolled a little tiny bit more, like maybe 1 rotation through the whole course. And the other one pretty much just slid across the surface. Now that leaves an open question. Sliding isn't for free, right? And you know that, okay, it's, there's still friction. It's still got mass. It's still sliding across the surface. It's still bumping into the surface. But you'd have to argue, okay, it's less friction. But you don't know how much less. You could spend a great deal of time trying to analyze exactly how much energy is being consumed and how far something could slide. It can't slide an infinite distance, so it's obviously going to lose energy sliding. So maybe in the end it's the same. But obviously any rotation is stored energy, so again, it takes extra energy to start making something spin. And it's going to be energy you have to produce. It has to come from somewhere. But anyway, by the way, the experiment was, the results were 19 and 11. Not very close, okay, to 1.4 in the sense that the ratio is pretty close to 2 to 1. And that would validate momentum as being completely in control of the experiment. Now, I would argue that he didn't compensate for the weight of his lever. He didn't put the location a little tiny bit in further. He didn't do a lot of those things that probably would have made the experiment more perfect in terms of isolating the variables and extracting them as an influence. But it's a real question, right? So anyway, so I guess the one solution to that problem would be to do just throw it into air, okay, because air isn't much of a friction source. So you eliminate a lot of the problems. So you do the experiment off the edge of a table, okay, and let the objects fly off and fall to a distance. And that should be a pretty good experiment, right? So you take your lever And maybe you could put a spring on here to get the same results each time. Just bend it back, launch it, and so you launch the 2 mass, you launch the 1 mass, and you see, okay, if this is actually going twice the velocity, because it'll go twice as far. And if this is going 1 velocity, then it'll go half as far. And that's probably the safest way to do the experiment. You just have to make sure that this launching surface isn't particle board or some kind of other rough surface that's obviously going to steal some of the energy, create drag. So you want to launch them off a sheet of glass here. You put a sheet of glass on top of the table, so you got a very smooth surface, very little friction, very little loss of the energy. Now, physics should have done these simple experiments, right? Are you going to argue? Is somebody going to argue that physics should have never tested any of this stuff? They claim the existence of it. They claim this lighter object, half the mass, only travels 1.4. So let me just illustrate. 1.4 is here. So instead of going here, okay, twice the distance. Well, this isn't twice the distance. Let me just move the table over here. All right. Now we're at twice the distance. So here's the distance table from the table. So here's 1 unit of distance. Here's 2 units of distance. This is where they say the half mass goes here. So it has half the mass. It should conserve all of the momentum. There's nothing about this lever that says I can't conserve momentum. And yet you're going to argue this is where it lands. And I'm saying it's a ridiculous argument. And why hasn't physics done the experiment? I mean, they've had forever to do it, right? This isn't that complicated, right? I mean, Steve Mould can't do this. Yeah, no, he can. And he won't do it, though, until you tell him to. Until somebody besides me says the physics should be evidenced and well evidenced, it's not going to be. It's just going to be a religion. And maybe that's what you want it to be. I mean, I can only assume you have some reason to support mv squared. I mean, Leibniz believed in solitons and monads and was a insanely he might as well have been a member of the Inquisition. He thought all human problems were caused by atheism. All of them. Yeah. So it would be a perfect world if it wasn't for atheists. That was the core of his shitty mindset. The guy who invented this absolute nonsense. And let's understand the absolute nonsense. I mean, we've been over it so many times, but I mean, how can you people defend this as being at all logical? I mean, it's 9.8 meters per 1 unit of time. 1 second is the unit of time we're using. It wouldn't be 9.8 if it's some other unit than a 1 second. If you make it a half second, then it's 4.9, and you know, it completely changes the number if you change the denominator. If you change the fraction, if you change the 1, then the 1 unit of time, you have to use a different number. And so the obvious truth is that it's just so easy to understand. Okay, this experiment is exactly the same as this experiment. Right? I mean, there's no difference. It's the same thing happens in the gravity. It doesn't matter how high up it is, right? I mean, the higher you go, the less gravity there is. But obviously it takes you have to go quite high before the gravity starts changing significantly from 9.8 to 9.7 to 9.6. You have to go like a mile or more, 3, 5, 10 miles. Anyway, and so this is 1 unit of time. This is 1 unit of time. And this will be exactly 1 unit of time also. So in the same time, you'll get one more unit of gravity. So the same amount of gravity you got here, you're going to get here. So let's just say this was, well, we're doing the 9.8 in 1 second. You're going to go 4.9, okay, in that 1 second. In 1 second, you'll travel 4.9 meters. This would be 4.9 meters. But you're going 9.8 meters per second. So even though you only traveled 4.9, it took you a while to accelerate, so that's why it's only 4.9. but you're going 9.8, and obviously I'm already doing that. I already got that here. The energy to get all of this I got from here. Okay, this unit of time gave me the 9.8 velocity. The 9.8 velocity is what's giving me these 2 units of distance, so I don't need any force to help me to get those. Those I would get if gravity stopped. I'd still get those 2 units for free. And the only one that's getting added is this, another 4.9 and another 9.8. So now I'm going 19.6. It all makes sense. I'm going twice the velocity. It all makes sense. And their claim is that even though it's 2 units of time, even though it's only 9.8 per 1 second, 1 unit of time, and I only went 2 units, and I'd only have 19.6, they're saying I got a full unit of energy here, and a full unit of energy here, and a full unit of energy here, and a full unit of energy here. They have 4 units of energy. I mean, you can't see how that's not possible. That's nonsense. It's idiotic. You can't get more motion from a stream if you spend less time in its current. I mean, you can understand if it's only 2 units in the current can only push me 2 units worth. If I'm in the current for 4 units, well, then I'm going to really be moved down the stream. I'm going to go a lot faster than 19.6. Oh, it's just so bad. How people can't understand. Look, it's half the velocity. Again, just like the rolling argument. It's 1/2 the velocity, 1/4 of the voyage. Truth. Actual fact. And you're saying it's some sort of proportional force? That I got the same force here, and the same force here, and the same force here, and the same force here. Yet I'm only going half the speed after just 1/4. How could it be the same force each one of these units when I'm going half my velocity? Either 3/4 or 1/4, depending on how you look at it. It doesn't make any sense. It's obviously not linear. It's just terrible. You can't understand these arguments? Ugh. Alright, just a short update on the Daniel Walsh character. So I did just post a link to my response video. I've created a response video, posted here, and I gave the link. And he deleted it. Okay, so that's fine. So at least he saw it. Alright. And so let's just understand. So this character makes a video saying even that levers are even more inefficient. So in the 2-to-1 circumstance, you don't lose just 30% of the momentum, you lose 50% of the momentum. That's how idiotic this moron is. So he gets the argument even more wrong than Steve Mould, and pretensively behaves as if he's doing something rational when it's just absolute nonsense. And again, nobody calling him out on that nonsense, which is revealing. Again, that you're not really just stupid. You're belligerently stupid. You're doing this on purpose. You're cheating the truth on purpose. Alright, so just for commenters, there's really no point. I'm not going to argue minutia over and over and over again in text. Not going to happen. So if you can't provide an experiment for me to debunk, and an experiment done by a physicist, okay? If it's not done by a physicist, not done in something called some kind of professional lab, then I'm not interested. And clearly we've already been over the air cart crap and the wheelie car crap. So if you can't come up with some better experiment, a ballistic pendulum or something like that, then just forget it. So show me a link to a ballistic pendulum experiment where they actually collect the kinetic energy, or anything more than the paltry momentum. So the momentum is always going to be a tiny number compared to the kinetic energy in any ballistic pendulum. So go ahead, just show me more than the momentum being collected. And if you can't show me, then just fuck off. Because if you're going to concede that you have some good reason to believe, and you don't have a single experiment with a ballistic pendulum demonstrating the collection of this crap, then what's the point of you arguing this crap is real? If you can't collect it, it's not real. Simple enough argument. All right. So the Paul Nord asshole. Sorry, Paul, but you're just you're just obtuse. He just keeps badgering on and on as if there's something about the calculation of the arc of a pendulum that is somehow insanely significant to measuring momentum. And there's nothing significant. There's nothing in the math that is at all making a grand statement of some kind about kinetic energy. You're just recognizing that this circumstance creates a fact regarding if you're going to measure how far something moves. So that's how you measure with a ballistic pendulum. You measure how far the pendulum moves this way. And you're because the amount of distance it's moving up is very, very slight. So it's very hard to measure. But the motion this way is very easy to measure. All right, so you have a very heavy mass moving a distance, and you just mark what its maximum distance is as a distance. And now you're just left with this simple process of calculating what that represents as a velocity. Now, the fact is if this was a piece of graph paper, and I did this carefully, this is all you have to do is draw it. You don't have to do anything other than just draw it. And you'll find that, okay, what's going to happen is that let's just say there's a unit of velocity, in miles per hour or something. And the argument's going to be is that, 1 mile an hour would look like that, and 2 miles an hour would look like that, and then 3 miles an hour would look like that, and then 4 miles an hour would look like that, 5 miles an hour would look like that, and 6 miles an hour. And it's just going to get tighter and tighter and tighter and tighter and tighter. So the distance as you go this way, quite obviously, I've drawn this so many times, quite obviously, as you're moving this way, you're not going much up, right? But as you're going up this slope, you're doing this, okay, and you're doing very little of this. So that's the difference between this slope argument. So this is a lot more work, because you're going to be going slower and slower. You're going, you're decelerating. So your velocity is decreasing, okay, and as you're going up, and so your time in the gravity is increasing per unit of distance. The work you're doing is increasing. So it's just like the friction argument. It's not linear. When you're going fast, there's very little friction. When you're going slow, there's a lot of friction because you weigh a lot more on the surface. All right. So we know that's the proportion. And we know that, okay, instead of half the velocity being here at the halfway point, okay, at 45 degrees, okay, we know, it's going to be 39 degrees. I think that's the number, actually. So that's where you're actually going to be going. That's where the point would be, okay, if you were to go drop something from here and you wanted to go half as fast as this is where you drop it from. And you can kind of see on the chart, that's not half. That's not even close to half the distance. It's a huge difference than half the distance. So if you're going twice the velocity, let's say a 2v gets you to this point, okay, 1v gets you to this point. That's how it works. So, it's 1v, 2v, all right? It's obviously not, anything like linear. So, but that's all it is. All you're really saying is, look, if I wanted to calculate it, I just figure out where the line is, okay, for what I want to have happen. I figure out this is 4 times as high from, say, this distance. So the first object I test does this. I know that it's going to be twice the speed. It'll be 4 times the height. So I just find where 4 times the height is, and I say, okay, that's the spot. So I can just do it as a geometric relationship. I can just draw it and get the answer. I don't have to do any math. But I'm clearly not objecting to the math. The math is just taking this angle, okay, and using the angle in radians as an argument, I think it's 2/3 something. I can't remember the exact formula, but it doesn't reveal anything. The formulation is just recognizing that this curved line has a consequence, that circles have a consequence in terms of how you're changing from this to this, okay? And that's all it's showing you. It's showing that the linear motion has little to do with rising in the beginning, and then later the linear motion is huge amount of rising. For any motion this way, you go a huge amount that way. And in the other case, it's exactly the opposite. So, there's nothing to argue here. But he wants to say that somehow, even though the absolute fact is when you do the ballistic pendulum experiment, you're going to lose. If I do 2 to 1, which is just simply saying let's do the 5 pounds, the 5 cart going 10, so I have a 5 mass going 10V, and then I add 5 mass to it, and I make a 10 mass going 5. They completely concede this happens. So there's no argument about this experiment in terms of the outcome, that the momentum is completely conserved, no problems at all. And I lost half the kinetic energy. So the ballistic pendulum, this would be the simplest ballistic pendulum. You're just putting a half mass into a 1 mass. Now obviously in most cases what you're doing is putting a 1/1000th mass into a 1 mass. Or 1,000 mass, 1 into 1,000 mass. A huge differential. So the amount of kinetic energy you're losing is gigantic. So as Professor Lewin draws on the blackboard, quite honestly, 99.94%. That's the reality. 99.94% of the kinetic energy doesn't get revealed. Okay, the ballistic pendulum can't collect it. That means it can't use it. It means it can't do work with it. So you can claim it has 2,000 joules of energy, but what does that mean if it can't do any work? If I can't do 2,000 joules of work and I can only do 2 joules of work, aren't you talking shit? And like I said, I'm giving you the benefit of the doubt. Obviously, it reveals that there is no such thing. That it's phantom energy. It doesn't do any work because it isn't real. It's a silly squared variable that shouldn't be squared. And again, I can go back to the electricity argument. I mean, it's such a correlation to any of you engineering types. Anybody who's played with electricity, you can sort of understand that it's almost the same kind of deal. Okay, I mean, you got the voltage, which equals the pressure, right? Right, and then you have the amperage, which is a clear correlation, okay, to mass. All right, so you can understand the amperage is the volume of stuff moving, and the velocity is the voltage is the velocity. It's really simple to understand it that way, and you'd understand that the watts, okay, which is the same as a joule, by the way, the watts are not going to require a squared velocity. That doesn't make any sense. It wouldn't make any sense. It'd be silly. So how come when electrons are moving inside of a wire, all of a sudden they can't do this inertia thing, they can't do any of this scalar energy thing? None of that's revealed. And you're stuck with, just the mechanics of momentum. Just basically saying that what you're passing through the wire in watts is just momentum of electrons. It's not the kinetic energy of the electrons. I mean, it's just a huge giveaway that this is nonsense, because it doesn't work in these other places where you can make a clear correlation that the two mechanisms are hugely related. Again, heat isn't squared. There's nothing. It's such bad science, and for you people to be so belligerent in defending the bad science, the lack of evidence, the lack of, the lack of doing any of these experiments. Again, in 300 years, they haven't dropped 4 pounds 1 foot and 1 pound 4 feet. 1 pound 4 feet is half the momentum of 4 pounds dropped 1 foot, half the momentum, and they claim it's the same energy. I mean, you've got to concede that doesn't sound plausible. You've at least that minimum, and say, okay, I want to see that, because that just doesn't work. How does something with twice the momentum fail to do twice the work? How is that possible? And where can I find an example of that? Something with half the momentum, okay, doing the same amount of work. Where can I find the example of something with 1/2 the momentum doing the same work as something with twice the momentum? Is there any example in reality? No. Alright, enough of a video. So the interesting thing is that, yeah, what's his name? Steve Mould. Is that his name? Steve? Yeah. Yeah, I've only made 65 videos. I should remember, right? Yeah, Steve. So he hasn't made a new real video. He's done a couple of shorts, but he hasn't done his next video. It's supposed to come out on Thursdays, it says on his channel, but obviously it didn't make it yet. So we'll see if it shows up today. And we'll see if he's going to fix what he broke, or whether he's just going to pretend he didn't break anything. He didn't cheat. He didn't defraud his poor, gullible audience with a nonsense video. And it was a nonsense video all the way through. I mean, he just didn't do anything honest or credible. And especially putting the minute physics clip in there, pretending that somehow pulleys validate broken levers, when no, they don't. They prove exactly the opposite, that your lever argument can't be true because pulleys conserve momentum. Alright, enough of a video. Till the next time and such.